Hi guys, it's Daniel here, and today we're going to take a small glimpse in a field of mathematics called algebraic number theory. Specifically, we're going to talk about algebraic integers. Now, what are algebraic integers? It may sound kind of complicated, but in fact it's quite simple. Given a polynomial, px, with leading coefficient 1, in other words, it's monic, and integral coefficients, like x squared plus 2x plus 3, then the roots of this polynomial is an algebraic integer. In other words, all algebraic integers are roots of some polynomial with integral coefficients and leading coefficient 1. For example, 1 is an algebraic integer because it is the root of the polynomial x minus 1. Square root of 2 is an algebraic integer because it is the root of the polynomial x squared minus 2. And I is also an algebraic integer because it is the root of x squared plus 1. However, numbers like pi and e are not algebraic integers, and we call these numbers transcendental. Of course, there are also other numbers that aren't algebraic integers, for example, 7/5, and these are called some other name like rational, perhaps. So, now that we know this definition of algebraic integers, let's look at some of the properties. Unfortunately, I won't be proving these properties because that's way beyond the scope of our little introduction here, but I will be showing these properties because they're pretty useful for solving problems. Okay, so now let's look at some of our properties. Properties. So, our first property is that the sum or product of any two algebraic integers is also an algebraic integer. So sum or product of any two algebraic integers is also an algebraic integer. So what I mean by this is that given an algebraic integer a and an algebraic integer b, these are both algebraic integers, then it follows that a plus b and a times b is also an algebraic integer. Note that this implies that a minus b is also an algebraic integer because you can clearly just take the negative of b to get a minus b, but note that a divided b might not be an algebraic integer. So be careful on that part. Our second property here is that the only rationals that are algebraic integers is the rational integers. In other words, the integers that we all know. What I mean by this is, given a rational number a, if it's rational and it's an algebraic integer, then it follows that a is in fact a rational integer. So these are the two most important properties of algebraic integers that we need to know for now. So now let's look at some of the problems. This is a problem from a Chinese TST from 2005. And it states that prove that the number square root of 1001 squared plus 1 plus square root of 1002 squared plus 1, etc., all the way to square root of 2000 squared plus 1 is irrational. Now, classical methods clearly won't work very well here, because if we try to square this thing and then try to square again to get rid of all the roots, nothing's going to happen. So, let's try to use our newfound knowledge of algebraic integers. Let's first look at this number. We note that this number is in fact an algebraic integer because it is the root of the polynomial x squared minus 1001 squared plus 1. And this is a monic polynomial with integral roots, integral coefficients. And similarly, this and all the way to this, these are all algebraic integers. So using our first property, we know that the sum of this is also an algebraic integer. So now we note that if the number is rational, then by our second property, this entire thing must also be a rational integer. So in other words, if we assume it's rational, then it implies that it is a rational integer. So now we just need to prove that this entire thing isn't a rational integer. And fortunately, this isn't that hard to prove, because if we just note that if this entire expression 1001 squared plus 1 square root that all the way to 2000 squared plus 1 square root of that is a rational integer, then if we subtract 1001 from the first part, subtract 1002 from the second part, all the way to subtracting 2000 from the last part, then this number is also a rational integer. Now we can actually simplify this part if we kind of like unrationalize the denominator, kind of like the opposite of rationalizing the denominator, and get that this thing is equal to 1 over the square root of 1001 squared plus 1 plus 1001. And this part equaling to 1 over square root of 2000 squared plus 1 square root that plus 2000. This goes over here. And clearly this thing is greater than 0. But we also know that this thing is greater than square root, greater than 1 over 1000 times 2 plus all the way to 1 over 2000 times 2, which in turn is greater than or equal to 1001 times 2 multiplied by the total number of terms in here, which is, this is 1001, which is 1000, which is less than 1. So this entire expression here is greater than 0 and less than 1. So that means it can't possibly be a rational integer. So therefore we have arrived at a contradiction, assuming that this number is rational, so therefore it is irrational, and we are done.
Today we're going to be doing more paper folding. This time it's going to be from AMC 10A of 2014, number 23. And